All right. Hello, Physics 135 students, and welcome back to our class number 4 lecture. So first, we're going to start out with another icebreaker. Today, the question is if you could have breakfast or brunch with any historical figure or fictional figure, who would that be and why? And I have not set up different threads in the Discord this time since I didn't really see any usage from the last lecture, although the quiz is not due yet. So if you all like the threads, do me a favor and send me an email. If you think the threads are a little extra, then I won't use them in the future. So you can also send me an email if you think that they're too much. Now, regarding my own answer, I haven't posted that in the Discord this time. So I kind of give a different answer every time I ask this icebreaker question. I would say today, it's a little cliche, but Einstein would be really, really cool. I met someone recently who was a kid while Einstein was still alive, and it struck him as being a really big disappointment in his life that he didn't meet Einstein. I didn't overlap with them. But it would be really, really interesting to hear in Einstein's own words about what he thinks about the development of the world these days, in terms of, his thoughts about relativity. That's documented pretty well in a bunch of biographies. I read Sir Walter Isaacson's biography of, actually, I don't know if Walter Isaacson has been knighted, but anyway, biography of Einstein, and I really enjoyed it. So, yeah, I would go with Einstein and pretty much to try to pick Einstein's brain in terms of quantum computing and kind of all the quantum weirdness today, see what he thinks of the resolution of the EPR paradox and other fun stuff. Okay, so for today, we're going to be going into the geocentric and heliocentric models. We have two different worksheets. The idea is that this lecture will be approximately 45 to 75 minutes long. Maybe I'll go 90 minutes. But the two activities that I have planned, I do think will take some significant time. Some students might blaze through them pretty quickly, but some students I think will need to, especially if you, for this Phases of Venus worksheet, you do this very carefully in order to do it correctly. It'll take some time, and kind of similarly for the retrograde motion activity. Not as much math, admittedly, in these activities compared to last class, but really important to uh, take careful attention and really be detailed in your work. Okay, so anyway, we'll start with geocentric and heliocentric models. Then we'll talk about really the scientific revolution that started with Copernicus, but was significantly advanced by Tycho, Kepler, as well as Galileo and eventually Newton. And then we'll talk about why we're kind of alternating here between first and last names. That's more of a joke, honestly. We'll talk about Kepler's Harmony of the Spheres, one of my kind of favorite, admittedly somewhat tangential, but very interesting facets that go a little bit beyond physics, but still very much of interest to me personally. We'll talk about Galileo and really the crucial role that Galileo played in advancing the heliocentric model and basically why people eventually accepted it. And crucial to this is the Faces of Venus, and we have a nice worksheet for you all to come to grips with that personally. And then last, we'll go into Newton's laws of motion. And regarding today, in addition to these two, worksheet activities, I have sprinkled throughout different attention checks that I'd like you to post in the Discord your responses to, and also please, please, please do email me for your responses to these attention checks. The first one is not really labeled as an attention check for the icebreaker, but it'd be great as instructed if you were to email me your response there as well. Okay, so moving forward, regarding retrograde motion and like the two models of the solar system, we'll start by trying to understand why the motion of the planets caused such a headache for ancient peoples. and then we'll talk about really why the ancient Greeks rejected the heliocentric model as being really a more simple explanation for planetary motion. So notice that we have AC1A and AC1B. In other words, over the next few slides, please make sure to jot down your answers to these two questions. Okay, so for the planets in ancient times, they weren't able to detect Uranus, Neptune, Pluto, etc. There were five visible planets in the ancient skies. Earth beneath our ground doesn't count, of course. So they were able to see Mercury, Venus, Mars, Saturn, and Jupiter. And admittedly, if we did have binoculars, it doesn't really take too much to be able to see Uranus. Neptune is pretty tough unless you really know where you're looking, and especially so for Pluto, which admittedly is not a major planet, but is still a dwarf planet. All right, and for our own eyes, maybe a lot of you have not actually seen Mercury yourself. Mercury is only really visible shortly after sunset and shortly before sunrise. Venus is similar, but you definitely have a larger time window. Venus is also one of the brightest stars. It used to be known as the evening star or the morning star by a lot of ancient peoples. The Greeks realized eventually that it was really just one object that they were alternately seeing in the morning and the evening. Mars is a very characteristic red color. It's kind of interesting that in the ancient skies for Scorpius, one of its brightest stars is called Antares, which means so Ares was, the name of the Greek planet equivalent to Mars. Antares means literally not Mars, in other words. And then we have Saturn and Jupiter. Jupiter tends to be pretty bright, Saturn occasionally bright. Okay, so we have our five different planets. Now, the part that was weird that the ancients recognized is that throughout the night, the planets, just like the stars, always move, east to west. But if you check where a planet is relative to the background stars, usually, the planets are moving faster, of course, than the background stars. In other words, the planets end up um, looking like they're moving eastward. Now, occasionally, Mars, and this happens with Jupiter and Saturn too, but it's most visible and most noticeable with Mars, that it will occasionally reverse its apparent motion from night to night, not during a night, but from one night to the next night. It'll look like it's going westward. So it has this kind of loop-de-loop pattern. And that was pretty strange. Like, why is Mars doing this? Why does this never happen for Venus and Mercury? And why is this admittedly happened for Jupiter and Saturn, but at a much smaller scale where it's kind of hard actually to notice it? Um, and regarding the models, so we've talked about Ptolemy last class. Ptolemy was not the first person, by the way, to come up with this geocentric model of these are the orbits of the different objects in the solar system. So in gray here we have the orbit of the moon, which is of course the closest circle to the Earth. Then Mercury was supposed to be second closest, then Venus, then the Sun, then Mars, etc. Ptolemy was not the first one to come up with all these circular orbits. They date back to Aristotle's time and even perhaps a little bit before with Plato. Um, Now, of course, the important part of the ancient Greek models is that they were trying to explain the world in a comprehensible way without invoking myths anymore. And in terms of the basic assumptions for this geocentric model, part of this, admittedly, still was a little philosophical or even you could say theological. So the first part, Earth being at the center of the universe, part of the rationale here that Aristotle was the driving force behind was that the reason why objects fell, whereas so-called heavenly or like air or like things like fire would rise to the sky, is because fire was pure and the heavens are perfect. So, in Aristotle's rationale, things go to their kind of natural home. There's a certain teleological explanation for motion in Aristotle's physics. So fire goes towards the sky since purity seeks purity. The reason why objects fall and why we are on the earth is because we are these kind of depraved fallen beings, not exactly Aristotle's words, but Earth was supposed to be kind of the celestial sledge pool. Um, so it was, in other words, although Earth was the center of the universe, this was not a privileged position. Now, in terms of the geocentric model, again, this was um, rendered in its most sophisticated and most predictively powerful form with Ptolemy. And Ptolemy's model was more or less cemented for 1500 years. That every few hundred years or so, it did have to get some updates, actually. And basically, every update, there were more circles that got added. And compared to this figure, Ptolemy's original model had 5 times as many circles. And by the time of the 1200s, again, there were some circles that were added as time went on to basically make sure that the model was still working. Uh, King Alfonso X of Spain had this really, I think, quite nice quote. If the Lord Almighty had consoled me before embarking on creation thus, I should have recommended something simpler. In other words, Ptolemy's model is just really kind of ugly, especially at the point of the 1200s. So there was a lot of dissatisfaction with Ptolemy's model. And regarding retrograde motion, the way that it explained retrograde motion is that the planets moved on circles on top of circles. So in other words, the reason why there was the loop-de-loop pattern of Mars is because Mars literally would move backwards for part of its orbit. And so that follows, but it does mean that there's this complicated kind of circle upon circle motion. And in fact, Ptolemy, as we talked about last time, Ptolemy recognized that the Earth had a varying distance from the Sun and the Moon. And so Ptolemy actually didn't put the Earth exactly at the center, but slightly displaced, along with another equant point, which was, so in other words, the circles upon circles were slightly displaced. In other words, this is kind of like proto-ellipses, but again, they didn't have the mathematics for solving, equations with ellipses until Kepler came along. So this was kind of like the best that they could really do with the mathematics that they had developed at the time. But really, it was a kind of complicated structure. Now, for us in our modern day, where we have ellipses and we have this heliocentric model, this was relatively easy for us to explain for apparent retrograde motion. Again, the idea is that now you're going to take a look at what retrograde motion would look like for the geocentric versus heliocentric models. So I want to before we have that actual pause, I just want to mention that the lectures kind of area is quickly growing in size. Maybe I should have broken this down a little bit more. Maybe I'll do that next time. Usually I have like week 1, week 2, week 3, and some students didn't really like that. So I'm switching it up this semester. So anyway, for class 4, pretty well marked. You can find the Aristarchus retrograde motion worksheet. And probably you'll want to work with the Word doc. And I would recommend printing this out if you can and doing it on paper. But if you do it digitally, if you have a tablet, that might be okay. For phases of Venus, that would be absolutely unacceptable. For phases of Venus, you really need to do it on paper unless you're able to use like rulers and protractors on a tablet. But doing it like on paint, like I'm not on a tablet, and I can use my finger actually on a touchscreen for my laptop, but that would not fly for the phases of Venus worksheet. Okay, so now it's time to pause the video and try to fill out that retrograde motion worksheet. Okay, so unpause. So we're going to go ahead and move on. Hopefully you did work on that retrograde motion worksheet. I'm expecting that that might have taken you somewhere between half an hour and 45 minutes, maybe a half hour to an hour. For some of you, you might blaze through it. It doesn't have nearly as much math, admittedly, as the Eratosthenes or other Aristarchus Sun and Moon worksheets from class 3. So you might go through it quite a bit more quickly, but I want to make sure that these lectures are not excessively long for the students that are really doing their best efforts. Okay, so in terms of why the ancient Greeks rejected the real explanation for the motion of the planets, in other words, why they thought that the Earth had to be fixed in its motion or lack of motion, and the main reason was that the ancient Greeks didn't observe stellar parallax. There were really like three major reasons, but this was really the kicker, I would say, and really what led Tycho to believe that there was a kind of quasi geocentric model in his picture of the universe as well. Um, so for parallax, we talked about this last class in terms of understanding the distances to the sun and moon. But the ancient Greeks knew that if the Earth was moving, then the stars should also appear to change in their motion if there are stars that are at varying distances. And due to the fact that they did not notice any motion of the stars, led to them to one of two conclusions. Either the stars are really far away, or the Earth is not moving. And they just didn't think that the stars could be that far away. Keep in mind that they really underestimated the distances to the sun and the moon initially as well. All right, so in terms of better understanding parallax, although we talked about this last time, we didn't have this demo yet, and I think that this is quite nice. So idea is step one, make a fist. Step two, make sure to rotate your wrist so that you can see your fingers. Don't like hyperextend your elbow or shoulder or something, but do it naturally. Okay, so now you cannot see my fingers on the screen, but I can see my fingers. Now open your pinky and try to hold it as close to your eyes as you can while maintaining focus. And admittedly for me these days, I probably should get reading glasses, I'm guessing, sometime soon. And then we're going to try to line it up with the 20 centimeter mark. And there it is for me, maintaining focus. And then we're going to close our eyes and blink back and forth. And for me, it starts out next to the 20 and then a little bit beyond where the 40 would be. But I would recommend doing this yourself. Okay, and then step two, now go ahead and stretch out your arm in step one. So make a fist, stretch out your arm like all the way, and then rotate so you can see your fingers. So again, you can see them on the screen, but for me to see them, I have to rotate like this. And then open up my pinky and then line it up with the 20 centimeter mark. This time, I really am in focus even better. So definitely my distant vision is okay, but maybe need some reading glasses. All right, and this time my pinky only moves to like the 28 mark or so. So clearly there is a big difference here. So in other words, the farther away something is, the smaller the apparent shifting that an object will undergo, and therefore the harder it is to observe that parallax. Um, and really, except for Aristarchus, the Greeks rejected that the stars could be really far away because they just thought that the universe was a whole lot smaller. And that is kind of a recurrent theme in this class, that the universe is a little bit stranger than we otherwise would have expected. And it's really um, maybe hard for us to think about today because there have been so many tumultuous changes throughout history. But by and large, people are kind of wrapped up in their worldview. It is very hard for someone to think or even hear something that they are not expecting. And so we'll try to work through some of those preconceptions or issues that you all might have as well. A lot of that I spend a rather more effort on in the solar system, though, especially for the phases of the moon, since essentially every student thinks that the phases of the moon are caused by shadows being cast on it, which is not correct. Okay, now regarding the heliocentric model, um, so hopefully you've done that retrograde motion worksheet, otherwise we have spoilers here. So the idea is that as the Earth is moving around the sun, it is lapping the outer planets. So the reason why Venus and Mercury never exhibit retrograde motion is because they're interior. In other words, they always end up lapping Earth. So if we were on Venus and we were viewing Earth, then Earth would have retrograde motion. But from our perspective on Earth, we don't see retrograde motion for the inner planets, but we can for the outer planets. And since Mars is closest to us, is the easiest to notice. For the farther planets like Jupiter, etc., they do experience retrograde motion, but it's really a smaller effect. Okay, so here is another attention check, or attention check number 3. So just a reminder that for each of these attention checks, make sure to pause the video as you get to your answers, post on the Discord ideally, and please, please, please do email me as well. So I'll let you all read this multiple choice question and then try to pause the video and get to your answer. Okay, so just to talk through this briefly, so stellar parallax um, is definitely true. So this is which of the following is not a fundamental difference. So C, this being expected in the sun-centered model, but not in the Earth-centered model, that is a fundamental difference. So it's not C, is what we know, because we're looking for the opposite. B, retrograde motion is real versus apparent um, for the geocentric versus sun-centered model. All right, so that is a true fundamental difference. And then A is also a fundamental difference. So D has to be the answer. And in fact, the geocentric model was not useless for predicting planetary positions of the sky. That's the reason why it persisted for such a long time, is because it was useful for predicting planetary positions, although it was kind of ad hoc that they had to keep on adding circles. All right, so the next step is we're going to learn about the Copernican revolution, both about some of the key pivotal figures that led this change fundamentally in the worldview of science, or the worldview of how people viewed the universe around us. And then we'll also address this question about Kepler's 3 laws of planetary motion, although this is much more of an emphasis in the solar system class. Nevertheless, Kepler's 3 laws of motion is really, his third law is really important in terms of understanding dark matter. Okay, so for Copernicus, the key date to keep in mind was really Copernicus' last year alive on Earth. 1543, Copernicus passed away. At the same time, Copernicus posthumously published a massive book detailing his heliocentric model. Now, the problem, and maybe part of the reason why Copernicus was so reticent about publishing, there is a lot of claims about Copernicus being worried about the church, drawing the ire of the church, although there were several other kind of pre-scientific monks and priests that had written something kind of similar to Copernicus, actually. So it's debated historically whether Copernicus was really the first to revive Aristarchus's heliocentric theory, which Copernicus didn't actually cite Aristarchus either. But nevertheless, in terms of the book that Copernicus did posthumously publish, that was the main source of not only inspiration, but of knowledge of a sun-centered model for many Europeans. So Copernicus, either way, did play a really influential role in the history of the scientific revolution. Now, again, part of the issue is that his model was no more accurate than the Ptolemaic model, and part of that is because Copernicus was still using perfect circles. After Copernicus, and as you all have hopefully read about in the book by the time that you watch this video, Tycho Brahe was really a interesting character, is one way to put it. Apparently, he had really rambunctious parties on his little private island where he had his observatory for many years. And apparently, there was a horse, or perhaps a mule, that was allowed to roam around free. He also had zebras and other exotic animals. But apparently, the horse was allowed to enjoy the wine and to party with the other um, nobles or other people that were some of the supporters of Tycho, and fell down the stairs and died one day. So kind of a sad element. Tycho was also a very fiercely, you could say, chivalrous person. Um, it's debated how historically accurate it is, but it's definitely a fun story. Supposedly, the reason why Tycho ended up dying is because he believed that the host, I guess this is part of the common etiquette at the time, the host should not stand up from the dinner table while the guests are still enjoying a meal. And one of his guests just would drone on and on and on telling stories. And Tycho apparently had too much wine to drink at one of these dinner parties, ended up really straining his kidneys or his bladder by holding in his need for biological function. And apparently that caused like kidney failure, kidney disease, and he ended up dying. Now that's really debated. He also had like a lead fake nose. He uh, challenged his uncle to a duel. He ended up losing the duel. He got shot in the nose. He didn't die. Thankfully, I guess it was more of a glancing blow or so. And part of the reason why he died is apparently he, challenged his uncle to a duel because he felt like his honor was affronted. But Tycho also didn't want to kill his uncle, so he refused to shoot as well. Kind of a very quixotic character. But Tycho was one of the most fantastic observers of this time period, and really for the past few thousand years. Now, part of this was due to developments with technology. And although there was not the telescope in the time of Tycho, there was the astrolabe. There were these mechanical devices that Tycho used for making very precise measurements. And for planetary motion, he was able to get these down to arc minutes, which is basically the size of like our cuticle when it's exactly held out. So the amount that our cuticle, in other words, just the like little tiny white part of our pinky finger compared against the sky, that's about an arc minute or so. It's a 1/60th of a degree is another way to put this. All right, and so Tycho again came up with this kind of weird model where he thought that the planets went around the sun, but thought that the Earth still had to be stationary because he still didn't detect stellar parallax and thought, if he can't detect it, then no one can. Um, Now, one of the most important things that Tycho did was hire Johannes Kepler as an assistant. And Tycho was very jealous of guarding his data. Actually, all that we know about Tycho's death and life really comes from Kepler's notes. And so Kepler suggested that Tycho died from this like bladder infection or kidney failure. Some people think that Kepler got really fed up with Tycho's antics. So Kepler was a very religious person. He didn't drink alcohol. He did not approve of Tycho's partying and again, Tycho's kind of strange behavior. Tycho also very jealously guarded his data and didn't allow Tycho didn't allow Kepler to analyze it as much. So there's some debate about whether Kepler might have poisoned Tycho or otherwise killed him. But that is left for historical speculation at this point. All right, so go ahead and now address this attention check 4C. Go ahead and write down your favorite historical anecdote about Tycho. I mentioned a few there, but there are many, many more in the readings. Okay, so pause the video and handle that. All right, unpause. So moving on. So on to Kepler now. And Kepler was really important because in addition to Tycho being, this fantastic observer that constructed the best data available at the time, Kepler was a fantastic mathematician or more of an analytical person. And at first, Kepler still tried to use circular orbits. Again, Kepler was a very religious person and thought that circular orbits had to explain the heavens, which should be perfect, like in that Greek worldview that was carried on with Kepler as well. But Tycho's observations seem to rule out circular orbits with the 8 arc minute discrepancy. So, in other words, 8 times the limits that Tycho is down to get to. So now, if you or me were to say what time it is, we might round a few minutes, right? So the question is, uh, how trustworthy was that 1 arc minute accuracy? If it was really more like 3 or 4, then you're only a factor of 2 off. Maybe, in some cases, if Tycho's average accuracy was 4 arc minutes, maybe sometimes he'd have an 8 arc minute issue. But Kepler, although had Kepler had a deep disdain for Tycho's lifestyle, still respected Tycho tremendously as a scientist, or tremendously as someone that really paid careful attention to detail. And so Kepler came to this conclusion really admirably that the observations were counter to his hypothesis of circular orbits. And this led to a total change in astronomy. So Kepler was really one of the pivotal figures in developing the mathematics of ellipses. There was, developments, I should say, before Kepler, but Kepler was really pivotal in terms of advancing that mathematics for predicting planetary motion. So, in terms of a circle versus ellipse, the idea is that an ellipse is basically a squashed circle. We can describe this with what's called the eccentricity, where if we have an eccentricity of 0, that means that the distance from every point on the circle is the same distance from the center. Whereas for a moderately eccentric ellipse, there is a varying distance from the center to like the minor axis compared to the major axis. And in fact, there are two focus points that have like a fixed distance ish when we get close. And this becomes more and more discrepant between the minor axis and the major axis as we get to higher and higher eccentricities. All right, and then for this next attention check, um, don't just pay attention to the slides, but please write down a description in words, ideally in your own words, as well as writing down like a diagram, like try to do a sketch. Don't just copy paste from the slides to help you better internalize Kepler's 3 laws. So Kepler's first law is that the motion of the planets around the sun is an ellipse, with the sun being at one of those two focus points, and there's nothing at the other one. Kepler's second law is that the planets move basically faster the closer they are to the sun, but phrased a little bit differently. The way that Kepler's second law is more rigorously stated, planets carve out equal areas in equal time intervals. So the areas refer to the planet moving from one spot to another in, say, 30 days. And then we can transform this into a triangle, for example, and the area of a triangle is 1/2 base times height. And then 30 days when the planet is farther from the sun, it doesn't move as far, but this direction is a lot larger, and that compensates. So the areas are equal. And the result of this is that the planets move faster the closer they are to the sun. And this is highly exaggerated. Most of the planets' motions in the solar system are very circular. The eccentricities are actually very, very small. And it could be that we would have developed much more rapidly as a technological civilization if our planets were a little bit less circular. It's something kind of interesting to what if think about. All right, and then Kepler's third law was expressed really more quantitatively now, that the relationship between the orbital period, in other words, how long it takes for a planet to move around the sun from beginning point to end point in its ellipse, is that squared is equal to the average distance from the sun cubed. Really, this average distance is the semi-major axis, but we can frame that as the average distance here. All right, and then in terms of a diagram, it's a little bit harder to have like a nice diagram for Kepler's third law. But in terms of this orbital period squared versus average distance cubed, if we were to do a linear plot, you have something that ends up looking curved. And admittedly, this is the speed, not the period. Really, the average period is going to increase as the average distance is increasing. The speed is inversely related to the period, which is why we have this decreasing. But if we square our orbital period and cube our average distance, then we'd expect a line. And in terms of measurements of the solar system that have, progressed from Kepler's time to very, very high accuracy, we do find a very, very good fit to the linear prediction in this, modified space, so square of the y-axis cubed of the x-axis, we do find a very, very good fit to Kepler's prediction, or Kepler's third law there. All right, and now for another one of these attention checks, and this is kind of important in terms of being able to handle the quiz as well as maybe some future exam questions. So go ahead and pause the video and try to address this problem. Okay, so unpause. In terms of using Kepler's third law, so we're talking about an average asteroid is maybe 4 AU. So we have 4 here. We can cube that. That'd be 64. The square root of 64 is 8. And you can use a calculator if you need help with what 4 cubed is or the square root of 64. That's fine. So our answer here is B, excuse me. So it would take 8 years. So being able to do squares and cubes and square roots, at least on a calculator, that is something that I'd expect in terms of this class. Again, requiring a high school level mathematics background. You don't have to do calculus for this class, although a lot of you are physics majors and we'll need to later, but not all of you are. All right, and so Kepler, in addition to coming up with the 3 laws of planetary motion, which are still applicable today, Kepler, again, was a very, again, religious figure that had a really hard time coming to grips at first with the motion of the planets not being perfect circles. Now, we have mentioned before, although briefly, that not Plato, but Pythagoras came up with this concept of musica universalis or cosmic harmony. There are lots of different phrases here. Now, really, Kepler is the one that came up with more music of the spheres or harmony of the spheres for a reason that will become clear a little bit later. But to go into a little bit more detail of Pythagoras, so Pythagoras, in addition to coming up with the Pythagorean theorem relating the lengths of these different triangles, lengths of the side of a triangle specifically for right triangles, Pythagoras also realized mathematically that if you have a string that is 2 times shorter, it is exactly 1 octave higher. In other words, it sounds like the same note to our ear. And Pythagoras recognized that if you have other simple ratios of strings, they produce consonant sounds, as we've talked about before. Now, regarding the sun, moon, and planets, if they also have simple ratios in terms of the radii of their circular orbits, then that would mean that they each have their own kind of unique hum in terms of their the frequency of them moving around in a circle. So Plato came after Pythagoras. Plato said that astronomy was for the eyes as music is for the ears, and in other words, called these twin sciences. So, in other words, there's a relationship between astronomy and music, at least according to Plato, which I think is quite nice. And now, in terms of Kepler, again, Kepler came up with his laws of planetary motion. And just like Copernicus came up with a huge, huge, colossal book describing his model, Kepler came up with a huge, huge book that was largely rationalizing why we could still have the heavens being perfect even with elliptical orbits of the planets. And in terms of that, the one of the books that he wrote was Harmonices Mundi, or again, like the harmony of the worlds. And what Kepler pointed out is that if you have, in terms of like 3D objects, you can only actually have perfect, they're not polygons exactly, but you can only have perfect 3D regular objects if you have elliptical orbits. And so we'll see kind of an example of what that means a little bit later. And then what Kepler also pointed out is that for elliptical planets, their motions are actually even more musical, if you will, than what Pythagoras suggested for circular orbits. Now, because there is a difference in the angular speeds of the planets when they get closer and farther from the sun, you can take ratios of the minimum and maximum speeds, and you end up with additional harmonies. So in this case, we have Mercury being a minor tenth. Venus is almost perfectly circular in its orbit, so it'd be just a single hum still, whereas Earth would be a semitone. And as a result of the different orbital periods, Kepler suggested that we have two bases in our solar system, Saturn and Jupiter, one tenor, two altos, and one soprano. And in terms of, again, Kepler's idea here, in other words, the motion of the planets should be this ever-changing song, whereas for Pythagoras, you just have single notes that I think would start to grate on the senses with time. And this is moving forward a little bit, but this is, I think, even a little bit more obvious when you consider the very nice kind of orbital resonance that occurs for the so-called Galilean moons of Jupiter, which we'll discuss pretty soon. So in terms of the orbital motion of Io being 1.8 days, if we were to convert that to hertz, which is per second, this would be, less than 1/1 millionth, or excuse me, a little about 6 times greater than 1/1 millionth per second. So in other words, this is an extremely deep note, much deeper than the deepest note a musical instrument can produce, which is called the octave bass. And then there is a very nice video of this, which we'll take a look at. And it looks like oh, here we go. This System Sounds, it was not created by me, of course, but this is also video applicable by YouTube. And then I'll pause this video occasionally, but I think it's really quite nice. So we're gonna let this play out, and you'll get to see if we were to ramp up the motion of the moons of Jupiter to audible frequencies, what this would sound like. And you can see, by the way, there are these regular polygons, again, related to the elliptical, ultimately motion of these objects, not perfect circles. All right, so hopefully you all can hear that. It's maybe a little bit quiet, but you can see that there are colors for the different planets, and then there's this kind of constant violet or purple area that's just kind of saying that, okay, whenever one of the moons of Jupiter passes this 6 o'clock position, if the motion is a clock, the 6 o'clock position, then there will be some sort of beat that will be higher if the motion is closer in and a bit deeper if it's farther out. All right, so back to this visualization now. And then it changes the color based on which moon had most recently hit it. All right, and then what's happening is that this is being ramped up to faster and faster speeds. So again, Io, the closest in moon, in reality takes 1.8 days to go around Jupiter, whereas you're seeing Io move around Jupiter in a few seconds, and now this is being increased in terms of their kind of orbital speed or fast forwarding through time, if you will. All right, so really pretty fantastic again. I really love that audio or visualization. If you've taken classes with me, you've probably seen this before, but I really, really enjoy it. Okay, so back to the slideshow, back to our show for today. So in terms of Galileo, moving on from Kepler, uh, so Kepler did a lot of great work in terms of overcoming kind of one of those kind of issues, but really Kepler still said that the heavens should be perfect. And a lot of people still disagreed with Kepler. They weren't as enamored by the harmony of the worlds or harmony of the spheres, and thought that circular orbits were still inferior to elliptical orbits. And that was one of the arguments that people gave for rejecting the heliocentric model. And really, the two other objections that were faced by scientists at that time, um, or by other scientists for that matter, were two other really Aristotelian worldview items, which were kind of sensible given the physics that Aristotle had suggested. And that was that Earth can't be moving because if the Earth was moving, like when we move through the Earth, we feel a wind. If the Earth was moving rapidly around the sun, then there should be this huge worldwide wind that would sweep all the birds out of the sky. It would be, how could it be possible that the Earth is moving thousands upon thousands of miles per hour if we don't notice it? So that was one of the issues that they were dealing with. And then the third issue is, of course, with respect to stellar parallax still. And Galileo really helped to address all three of these items and really came to really some awesome solutions. So for this first objection, Galileo did a large number of experiments. Like Tycho, Galileo was an experimentalist. And as a result, Galileo showed that really objects seem to have some principle of inertia, which Newton really helped to clarify a little bit later, as well as more mathematically. Kind of like how Tycho was the observer and then Kepler was the mathematician. In many ways, Galileo was the experimentalist, and then Newton helped to solidify things theoretically. And this happens in terms of the theory of electromagnetism as well. It's kind of interesting about this lockstep between really, I would say, observations driving requirements for our change in our worldview, and then a theorist coming along to explain everything. And often the theorist is kind of more famous than the observer, but Tycho is really key to Kepler's work in the same way Galileo was really, really key for Newton's work. All right, so in terms of understanding how Galileo showed that objects would stay in motion, there are two really, I'd say, nice video demonstrations, and they're both pretty short. The first one, a little bit out of order in terms of the slides, but the first one I like to show is a B-2 bomber. So back in World War II, there were a lot of issues, even though this was way past Galileo's time, there's still a lot of issues in terms of understanding for pilots when they should drop bombs. That a lot of pilots were still stuck in this Aristotelian worldview, even during World War II, that, I need to wait until I'm over the town because the bomb's going to drop straight down. But that's not actually what happens. The bombs actually keep the velocity of the plane, and so that's why they're not trailing backwards. There's not a lot of air resistance because these things are really, really heavy for those shells that they're dropping. Instead, they keep the velocity of the plane. And so, in other words, pilots need to drop them before they're over their, vertically over their projected target. And again, that caused issues in World War II. There was a lot of bombing that was performed, but not a ton of it was effective. It was cumulatively effective, but it took a while for pilots to get used to this. All right, and then the other, I would say the smoking gun evidence that really solidified Newton's first law of motion, or in other words, Galileo's um, principle as far as objects not getting left behind, was in 1971 with the Apollo 15 mission. So again, I'm going to shut up, and it's only a minute long. We'll go ahead and take a look at what the Apollo astronauts are saying. So, by the way, there's a voiceover. So this is Commander David Scott, and the mission controller is narrating this.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo.
Great. So very, very cool. So we have really experimentally proved that objects do not, so the feather, in the air is left behind. And that was part of Aristotle's idea is that the feather, is more like air, and therefore it wants to stay in the air. Whereas on the moon, there is no air, right? And so that kind of proves that there's nothing kind of special about the feather having some air-like attribute that prevents it from falling to the ground. It's just that air resistance provides some repulsion to gravity, as you all would know if you've taken intro physics um, with friction, and otherwise we'll learn about at some point. So back to our slides. Okay, so Galileo handled the first objection regarding why objects are not left behind in the air if the Earth is moving. In other words, the atmosphere is not stripped, birds are not removed from the atmosphere because basically everything is moving with the Earth. And we'll revisit this when we start talking about special relativity. For the second objection, I want to stress that Galileo did not invent the telescope. Hans Lippershey is credited for having the first patent for a telescope. It's kind of debated about who really invented the telescope first. There were a lot of people around the same time that were making them. But Galileo, for one thing, significantly improved the telescope. He made his own about 6 times better than previous iterations. And Galileo was the first person to point his telescope to the stars, or in this case, to the moon, and noticed that there were craters, or in other words, imperfections on the moon. Galileo also pointed his telescope, perhaps somewhat unwisely, at the sun, and Galileo ended up going blind, um, possibly because he ended up staring at the sun a little bit too much. Now, in terms of how he noticed sunspots, he was probably primarily viewing the sun very close to sunset or to sunrise. If you've been on a beach and have, tried to look for the green flash, then you've realized that when the sun gets really low on the atmosphere, it doesn't seem to hurt our eyes. And at a certain point, I'm not a medical doctor, by the way, but at a certain point, I think that there is so much atmosphere that probably doesn't hurt your eyes too much. But you still want to be careful. Galileo did go blind for some reason, probably related to looking at the sun too much. Okay, so Galileo looked at the heavens and showed that they were not perfect. In addition to them not being perfect, the other part of the Aristotelian mantra was unchanging. So the idea about meteor showers was that those were just purely atmospheric aberrations, that meteor showers didn't have, and in fact, meteor showers are related to objects, moving through our atmosphere, so fair enough. Now, Galileo showed that there was change in the heavens, though, and that change was related to the so-called Galilean moons. So Galileo observed that there were these stars that appeared to be changing in their orientation around Jupiter. And kind of fantastically, the original manuscript for this is at the University of Michigan Library. It's not Purdue University, but I go blue. I did my PhD at Michigan, so I got to view this. It was very, very wowing to feel drawn back to roughly 500 years, excuse me, well, so about 400 years into the past, and one of these key moments in astronomy. So the discovery of the Galilean moons, or Galileo's discovery, excuse me, of Jupiter's moons, showed that the heavens were not unchanging. There was motion, and if there was objects moving around Jupiter, that suggested that not everything revolved around Earth precisely. So regarding parallax, item 3, Tycho thought that he had ruled out parallax because he didn't notice any distinction to stellar distances. He thought he had worked out the distances to the stars. Galileo pointed his telescope to the Milky Way and found that out that Tycho was evidently wrong in this one case, at the least, because the Milky Way ended up being thousands upon thousands of individual stars, not just this so-called, well, Milky Way. And therefore, if the Milky Way is a bunch of individual stars that were just too distant to resolve with the naked eye, that means the stars had to be really far away, and therefore it's unsurprising that there was no parallax. And then this was finally kind of resolved with Barnard discovering one of the objects that has the most proper motion in the sky, demonstrating actual parallax. But that was quite some time after Galileo. Now, what I would consider really the most conclusive test that Galileo also pointed out was related to really a key distinction between the predictions of the heliocentric model and the geocentric model. So again, in terms of the phases of Venus, you can find these on Brightspace. In terms of the phases of Venus worksheet, I've modified this a little bit from 2 years ago. So if you've done this activity before, make sure you carefully read the instructions. The main thing is I tried to make one or two items a little bit more clear. It hasn't changed very much. But please be as careful as you can. You must use rulers and protractors to make sure that you have straight lines as well as perpendicular lines. That means that you have to have one line at one angle, another line 90 degrees from it. And just me moving my mouse, that was not good enough, right? You really need to use a real protractor for this. So on this second page, this is for the geocentric model. And yeah, do the best job that you can. This is exaggerated to try to make sure that Venus is not too tiny for you all to do these drawings if you print it out. Um, so keep in mind that this is a little bit exaggerated. Ideally, Venus would be doing a smaller circle. And then we have the heliocentric model. So I'd like for you all to pause the video and to complete this Phases of Venus worksheet now. Okay, so video unpause. And if you're not pausing the video and doing the worksheet, you're really doing yourself a disservice. The idea of these worksheets is to help you better understand this material, like with your own hands, with your own tactile feeling behind it. All right, so in terms of, now it's a spoiler, so hopefully you've done it. But in terms of the geocentric model, or the Ptolemaic model, if you prefer, then again, you might have come up with like quarter phases of Venus, or maybe even somewhat gibbous phases, because again, my diagram was a little bit, was really exaggerated, admittedly, in terms of the size of the um, size of the circle upon the circle, or in other words, the epicycle. Now, nevertheless, you should never get a full face of Venus in the Ptolemaic model. And done more rigorously in the Ptolemaic model, there's only new and crescent Venus phases. In fact, there are two new Venus phases. Whereas in the geocentric model, excuse me, in the heliocentric model, in other words, in the Copernican view that was adopted by Kepler as well as by Galileo, um, in this case, there should be exactly one new Venus phase, and there's the same phases of Venus as we see for our moon. So there should be a full Venus phase. One thing to keep in mind, which I addressed on the worksheet but didn't mention before I asked you to work on it, is that in reality, the motion of the planets is 3D. So it's not like the sun is always blocking Venus. That happens very rarely, just like for the same reason that we don't have an eclipse every single full and new moon. Again, motion is 3D. And so Galileo observed Venus and observed occasionally full and gibbous phases of Venus. And this really put the nails in the coffin, so to say, for the Ptolemaic model and gave the strongest possible evidence for the Copernican view. Now, Galileo, I guess the saying is that no good deed goes unpunished. Admittedly, Galileo didn't only do good deeds, so to speak, in terms of the science. So Galileo was a fantastic scientist, but like many scientists, admittedly, if you will, with tremendous power comes tremendous responsibility. And Galileo got a little bit of a pinhead, at least in my opinion. So part of the problem is that Galileo was really, really good friends, like childhood friends, with this bishop, who later became an archbishop and then the Pope. And when Galileo's best friend became Pope, he thought, all right, well, I have a hall pass. I can say and do whatever I want, and I should be on the mend, should be good. Now, the Catholic Church was reeling with Protestant Reformation around this time. So keep in mind that Copernicus published in 1543. The Kepler was actually Protestant, um, which doesn't really matter, of course. So Kepler was not really concerned about the Catholic Church, admittedly. Galileo was Catholic; he was Italian. Like, and again, because of his relationship, he thought he could do whatever he wanted. He became very displeased when the Pope didn't immediately endorse the heliocentric model and still persisted in favoring a geocentric model. So Galileo wrote a book that explained his model to a more popular audience. It was meant to be a non-technical book and had arguments between someone who believed in the geocentric model, who was nicknamed Simplicio, but who had the same actual name as this Pope. And so it was clear that Galileo's book was really like was really like poking fun at his friend who is now the Pope. And unfortunately, Pope Urban VIII was not so gracious in this cartoon, if you will, that Galileo drew of him. And so Pope Urban VIII um, banned Galileo's book that made fun of him. He also ordered Galileo under house arrest. And one thing to keep in mind is that being ordered under house arrest, yeah, he was definitely punishing Galileo, but this was nowhere near the ancient torture devices that otherwise the church employed at that time. So, in any case, the church ended up reversing its stance in 1824, removed Galileo's book from banned books. And in 1992, Galileo was vindicated by Pope John Paul II. So there's this kind of back and forth, if you will, with Galileo and the church. I think the book does a pretty good job of explaining this. A lot of intro astronomy books don't go into the nuances quite as much. If you're interested, there is a very rich historical discussion that could be pursued here. And regarding the next part, I don't expect you all to really in detail study this, but the idea is to try to come to grips with these three objections that the world was kind of giving for the heliocentric model, and then how Galileo overcame those three objections. So suppose that you're Galileo and you're on trial, defend the heliocentric model. Don't necessarily defend his representation of the Pope as Simplicio, although you can if you want. That's kind of orthogonal to this class. Then second, suppose that your prosecutor of Galileo come up with counter arguments for Galileo's model or observations. This is meant to really tax your brain since we're very much in the worldview of the heliocentric model by and large today. And then third, suppose that your Galileo still try to defend yourself against, again, admittedly, your own prosecutor speech. And for this, it'd be really, really ideal if you did this on the Discord. And for the prosecutor, you reply to someone's AC6A, where they give Galileo's opening speech, and then it becomes again much more of a communal activity, like if this was in person. Okay, so my screen is going orange. I'm losing daylight here. So we're almost at the end, though, is the good news. Now, for moving on beyond Galileo, again, Galileo was this tremendous experimentalist, and really Sir Isaac Newton codified everything that Galileo developed and went much beyond that, developed a lot regarding optics and really laid the foundations for modern science, or modern physical science anyway. So Newton's first law of motion, there are many different ways to represent this. We'll say in this class That formally, Newton's first law of motion is that a body will continue in its present state of motion, either at rest or in uniform motion, until it is compelled to change by a force. Now, by uniform motion, keep in mind that this means constant speed and direction. That doesn't mean like circular motion, because then you're changing in direction. So, okay, so AC7A, try to explain Newton's first law, kind of ELI 5, so explain it like I'm 5. In other words, use very simple words. So a lot of you have commented that the AI used advanced vocabulary. This is kind of an anti-AI attention check, um, but not for that purpose. But try to use very simple words and try to explain the first law really just in 3 words. So as simple as possible. Okay, so pause the video if you need to, but otherwise let's move on. Newton's second law. We have one of my famous or favorite, I would say, Star Wars cartoons. Luke used the mass times the acceleration. So Newton's second law is that the acceleration of an object, usually people will say that Newton's second law is force is mass times acceleration. But really the force is more of is a little bit more cause, and acceleration is the more, I mean, force is kind of a derived quantity, acceleration is the more directly measurable one. So instead, I'd prefer to say that the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. So force is basically the cause, acceleration is the effect, and we notice the effect observationally. So in terms of what acceleration is, if you've taken intro physics, this should be intimately familiar. If not, though, that's perfectly fine. Acceleration is the change in the velocity, and that can be a change in the actual speed or the direction, keep in mind. And acceleration is really our way of quantifying how quickly a change in motion happens. So for AC7B, try to come up with 3 examples of an object accelerating. This could be a car, or it could be a rocket ship, or a football, or a soccer ball, whatever, or whatever you'd like. So 3 examples, please. All right, and pause the video if you need to. We'll go ahead and move on here, though. All right, so Newton's third law of motion. And this is admittedly the hardest one for students to understand typically. The idea is that whenever there is a uh, force from one object upon another, there is an equal and opposite force from that second body back on the first. So if you're ice skating or if you're on ice and you push on someone, then it's not just that the other person moves, but you both move actually. And same thing for like if you've ever shot a gun before, or for a lot of the students that have maybe been in ROTC or deployed overseas, if you've ever seen artillery fire, then not only does the cannonball or the artillery shell shoot out, but typically the cannon has some recoil. Now, for more modern artillery, they're built to be really, really beefy, where they don't move very much, but they still do at least vibrate and move a little bit. Or one of my favorite movies, in Wall-E, the reason that Wall-E is able to move with the fire extinguisher is precisely due to Newton's third law. And this is how all spaceships move, of course, in space. Since they don't have anything to push off of, they're moving due to Newton's third law. And speaking of rockets and spaceships, this is an image of Artemis 1, which was a flight test. It was uncrewed back a couple years ago, or back almost 4 years ago now. And Artemis 2, I'm very excited. It's slated to launch February 6th. We'll have to see. Sometimes there's clouds and they'll delay that by a day or two. But stay tuned for Artemis 2. This is the first manned mission to the moon in about 50 years or so now. So we're not going to land on the moon for Artemis 2. That's meant to be Artemis 3, but this will be the farthest that humans have ever gone from Earth before. So the for Artemis 2, it's going to be a flyby of the moon. So the rocket's going to go a little bit past the moon, and then they're going to come back. And there were, I'm a little bit worried because there were some heat shield issues with Artemis 1. It sounds like they've done a thorough investigation, so I'm hopeful, very, very hopeful that there are not any additional, you know, space fatalities from this. But yeah, so I'm really excited, a little bit nervous, but mostly excited, and definitely I'll be staying tuned in a few weeks when this happens. All right, and then beyond Newton's three laws of motion, Newton explained gravity, explained really everything from an apple falling from a tree, probably not actually on his head, but an apple falling from a tree, to the motion of the moon around the Earth and the motion of the Earth around the sun, being related to this so-called universal gravitational force, where the gravitational force is directly proportional to the masses and inversely proportional to the square of their distances. So for directly proportional, if you're not a physics major, or even if you are, maybe you haven't heard of this like phrase before. Idea with directly proportional is, let's say that we're trying to figure out how many Ferraris we can buy if we were Elon Musk. So let's say that we have a few $1 billion lying around. Now, let's say that the price of a Ferrari is $1 million. Now, I think that actually some of the cheaper models are only like 200 or 300K, still very far beyond my reach. Although I'm not that into Ferraris, I prefer Lamborghinis, just aesthetically. But in any case, let's say that Ferrari, or maybe more like a Rolls-Royce Phantom or whatever, let's say that there's some $1 million sports car that we're trying to buy. The more expensive that sports car is, the fewer we would be able to buy, right? Sorry, let's save that for later. Let's say that the number of dollars that we have increases the number that we're able to buy, right? So let's say that $1 million sports car, if we have $1 billion, then we can, buy 1,000 of them. If we have $2 billion, then we can have 2,000 of them. So the number of dollars that we have is directly proportional to the number of units that we can buy. Or excuse me, the number of units that we can buy is directly proportional to the amount of dollars that we have. Anyway, you get it. It goes both ways. In fact, it doesn't matter which way I say it. Now, put a different way. Let's say that inflation kicks in, and instead of our $1 million sports car, it becomes worth $10 million. That is a inversely proportional relationship. The number of cars that we can buy with $1 billion decreases if inflation drives the price up. Okay, so in other words, for the force of gravity, as the masses increase, the force increases. As the separation decreases, the force also increases. So that's why it's kind of the motion of the planets according to Newton's Kepler's second law. That's why the planets move faster when they're closer to the sun, even though the masses haven't changed. It's because the force is greater as the distance decreases, and that causes a greater acceleration, which means that the velocity changes more rapidly. Okay, and so we can see this for the motion of the solar system objects. So again, Newton has explained a ton, ton, ton. And we'll have one last attention check. The idea is that you all should try to identify each of Newton's three laws that are at play in these two scenarios, and keep in mind that each of Newton's laws could come into play more than once in these two scenarios. And so that's what we'll end with. So this lecture was about as long as intended, maybe a little bit on the longer side, but hopefully those two worksheets don't take you too long. The idea is to spend 2.5 hours total per week on the lecture material. So if you have any questions or concerns, please, please, please do email me or attend office hours. Hope that you enjoyed this class with all the videos and activities. Until next time, bye bye.